Hello. In the previous video, we showed how thermodynamics answers the questions that must be answered in the construction of any physical theory. Throughout these videos, we have stated that physical theories endeavour to answer the question, what is change? And do so by answering the slightly simpler question, what happens to a system when something external acts upon it? The first step in answering this question is to come up with an answer, is to explain how the system behaves in the absence of an external agent that perturbs it. In thermodynamics, we stated that an isolated system that has nothing external acting upon it remains at equilibrium with the values of all thermodynamic variables fixed unless it is perturbed by an external agent. In doing this, we introduced the notion of thermodynamic variables, and we introduced this distinction between extensive and intensive thermodynamic variables. We explained that that the extensive thermodynamic variables depend on the number of atoms in the system, and the values of the intensive thermodynamic variables do not. We then showed how we can use the intensive thermodynamic variables to characterize how the system responds when it is perturbed by the external environment. In doing so, we introduced the notion of a phase and said that it is simply a part of space. We can think of the system, a part of the universe, and its environment, the rest of the universe, as a particularly big two-phase system. We explained in the first video how we could characterize the state within some phase by noting the values of all the extensive thermodynamic variables within it. We then explained how, if this first phase is placed in contact with some second phase, and if the values of the intensive thermodynamic variables in these two phases are not equal, the state of the first phase, the system, will change. In other words, if the rest of the universe applies a force to the lump of material indicated by the blue box shown here, the material will stretch and its volume, an extensive thermodynamic variable, will change. We can thus characterize how the system will respond to an external perturbation, essentially being placed in contact with a second phase, by noting whether or not the values of the intensive thermodynamic variables in these two phases are equal or not. Our intensive thermodynamic variables thus characterize what an external agent will do to change the state of our system. We now come to one of the most critical ideas in thermodynamics, an idea that is, in my view, underemphasized in all of the textbooks on the subject. Temperature is an intensive thermodynamic variable. Let's consider what that means. Remember that I have insisted that the state of the system, the way that it behaves if nothing acts upon it, is characterized based on the values of the extensive thermodynamic variables, and that intensive thermodynamic variables are used to describe what an external agent will do to the system. That is to say, the intensive thermodynamic variables are used to say if there is some imbalance between the system and its environment. If the intensive thermodynamic variables in the system and the environment are the same, then the system state will not change. The system state only changes if the intensive variables in the environment are different to those in the system. Let's consider that for temperature for a moment. The fact that temperature is intensive and that this intensive variable characterizes a lack of equilibrium between the system and its environment is even evident in the way that we measure temperature using a thermometer. How does a thermometer work? Well, in the old-fashioned non-electric ones, there is some liquid inside a thin capillary. You place the thermometer inside the system. If you are taking the temperature of a person, you put it in their mouth or in some other cavity. The volume, an extensive thermodynamic variable of the liquid inside the tube, then changes and you read off the temperature. What you are actually doing, however, is reading off the volume of the liquid inside the tube, an extensive thermodynamic variable. By placing the thermometer inside the patient, what you have done is force the liquid in the tube, a phase, to come to equilibrium with the patient, a second phase. Obviously, during this process of coming to equilibrium, the values of the extensive thermodynamic variables in both the thermometer and patient have changed because these values characterize the state of the liquid in the thermometer and the state of the environment, the patient. To make this completely transparent, let's remind ourselves about this business of phases and phases coming to equilibrium. Let's consider the system of two phases shown here. The state of each phase is characterized by the set of values for the extensive variables. For example, the phase on the left, phase 1, has a volume V1, and the phase on the right has volume V2. Each phase then also has a value for the intensive thermodynamic variables. So phase 1 has a pressure equal to P1, and phase 2 has a pressure equal to P2. If these two pressures are equal, then the two phases are said to be in equilibrium, and the values of the extensive thermodynamic variables in each of them, V1 and V2, will not change. If, by contrast, the pressure of phase 1 is greater than that of phase 2, phase 1 will expand, and its volume will increase, while the volume of phase 2 will contract and thus decrease, Furthermore, because the extensive thermodynamic variables change, the phases will move to different thermodynamic states. As the volume of phase 1 increases, its pressure will drop. Similarly, as the volume of phase 2 decreases, its pressure increases. This process of state change in the two phases continues until the pressures in phase 1 equals the pressure in phase 2. Once this point is reached, the two phases are in equilibrium and their states are then fixed. Let's now consider this process with temperature. As discussed previously, temperature is intensive. Consequently, any difference in the temperature of the two phases will drive a difference in their states. If the volumes of the two phases are held fixed throughout, and if atoms are not allowed to move between the two phases, how do these changes of state manifest themselves? The answer is that we introduce a new extensive thermodynamic variable known as the entropy, S, to describe how two phases with different temperatures, which are not allowed to exchange atoms or volume, can come to equilibrium with each other. As the temperature of phase 1 decreases and the temperature of phase 2 increases in order to bring the temperature of the two phases to equality and the system to equilibrium, this new quantity, the entropy for phase 1, decreases and the entropy for phase 2 increases. Now, you might have heard a lot of bullshit about entropy in other places. For example, people might have told you that entropy is related to disorder. Yuck! Aside from being simply wrong, this is a completely and utterly meaningless statement. How is it related to a disorder? What does this statement even mean? Alternatively, I have heard entropy described as a quality of energy, which is equally pants. Please forget all this crap now. For the time being, we are going to define entropy as follows. Entropy is the conjugate extensive variable to the intensive variable temperature. We are then going to develop a more refined understanding of what this quantity is as we go along, that does not involve any nonsense about disorder or quality of energy. Let's think about this statement for a moment and explain what it means. This statement that entropy is the conjugate extensive variable to the intensive variable temperature. An alternative way of expressing this idea is as follows. Entropy is to temperature as pressure is to volume. In other words, volume is the conjugate extensive variable to the intensive variable pressure. What we mean by this word conjugate in this context is that if we have two phases with different pressures, and if we leave them to come to equilibrium, but do not allow them to exchange entropy or material, they will do so by changing their volumes only. Hence, two phases with different temperatures, which are placed in contact but which are not allowed to exchange material or volume, will come to equilibrium and an equality in their temperatures by exchanging this mysterious extensive quantity entropy only. To make this business of conjugate thermodynamic variables more clearly, let's consider two phases that can exchange matter between them. Each phase will be characterized by a number of atoms, an entropy, and a volume. We set the temperatures and pressures of the two phases to be equal, but observe material to flow between them. In other words, we observe the number of atoms in phase 1 decreases, and the number of atoms in phase 2 increases. Some intensive thermodynamic variable must be driving this flow of material between the two phases. The conjugate intensive variable in this case is another of these made-up quantities. In this case, we call it the chemical potential and give it the symbol mu. The flow of matter from phase 1 to phase 2 is driven by a difference in the value of this chemical potential between the two phases. In this case, the chemical potential in phase 1 is greater than the chemical potential in phase 2. As such, matter is passed from phase 1 to phase 2, and the chemical potential of phase 1 decreases and the chemical potential of phase 2 increases. This process continues until the chemical potentials in the two phases are equal and the system is in equilibrium. What I want to emphasize here is that in thermodynamics we need as many extensive thermodynamic variables as intensive thermodynamic variables, as every intensive variable must have a corresponding conjugate extensive variable. We thus introduce things like entropy and chemical potential to make up the numbers. This, I think, is the easiest way to think about these particular thermodynamic variables, entropy and chemical potential. These are there for mathematical convenience only. Unlike quantities such as pressure, volume, and number of atoms, it is not easy to explain what these thermodynamic quantities physically represent. Let's finish by briefly summarizing everything we have learned about equilibrium thus far. We have argued that we introduce the notion of equilibrium as we are interested in describing the nature of change. We've said that in physics, we state that change happens whenever something external to the system acts upon it. To understand change, we must therefore understand how the system would behave in the absence of any external agent driving its behavior. In thermodynamics, we thus stated that in the absence of any external influence, a physical system will remain in a state of equilibrium with the values of all its extensive thermodynamic variables fixed. We next refined this concept of equilibrium by thinking about multi-phase systems. In a multi-phase system, we explained how equilibrium is a state the system eventually settles into. When the system settles into this state, the values of the extensive thermodynamic variables in each of the subphases of which it is composed remains constant. Furthermore, the values of the intensive thermodynamic variables in each of these subphases are fixed and one value. In other words, the values of the intensive thermodynamic variables are uniform throughout the system. As a consequence, each of the phases in the system can be completely characterized by a small set of thermodynamic variables. To consolidate these ideas, we will in the lecture use them to prove Gibbs Phase rule, which states that the number of independent thermodynamic variables in any given multi-phase system is given by the expression shown here. Thank you for your attention.